Welcome back, and in this next video we're going to be looking at the solubility of the hydroxides and the sulfates of group 2, and we're going to go on and look at the thermal decomposition of the carbonates and nitrates. So as usual you're going to need your notes and a periodic table. So we're on page 8 of your notes and we're looking at the solubility of the group 2 sulfates and hydroxides. Just as a little aside, all group 1 salts are soluble. So sulfates and hydroxide group 1 compounds would all be soluble. It's only group 2 where there's a change in the solubility going down the group. And we can see that here. As you go down the group for the sulfates, they become less soluble. So barium sulfate is a thick white precipitate, whereas the hydroxides follow the opposite trend. They become more soluble as you go down the group. Now at this stage, all you need to know is the trend in solubility. You don't need to actually understand the reasons why. We will be studying those reasons in a pack called Solubility, which will be in the summer term. One way to remember this is that if the cations and the anions are similar in size, then the salt will not be soluble. If there's a big difference in the sizes, then they will be soluble. But please be careful. This is not an explanation. It is simply a way of remembering which salts will be soluble and which will be insoluble. So barium and sulfate ions are very similar in size, so they're insoluble. The hydroxide ion is much smaller, so barium hydroxide is soluble. Magnesium and hydroxide ions are again relatively similar in size, so they'll be insoluble, whereas magnesium and sulfate ions are quite different in size, so they're likely to be soluble. So we're now moving on to look at the thermal stability of the group 1 and the group 2 nitrates and carbonates. Now the stability of these salts depends on two factors again, the charge on the cation and the size of the cation. Please don't muddle this up with reactivity. Students often get confused between thermal stability and reactivity. For group 1 and group 2, the reactivity increases as you go down the group. The thermal stability also increases, so they become more stable as you go down the group. So as we go down the group, the size of our cation increases. Therefore, the thermal stability increases. As you go across the group from sodium to magnesium, the ion becomes smaller and the charge becomes higher. Therefore, magnesium nitrate and magnesium carbonate is much less stable than sodium nitrate or sodium carbonate. In other words, it will break down far easier. So we need to understand why the carbonates and the nitrates are less stable the further you go up the group. And the reason for this is it's to do with what we call the polarizing ability of these cations. So cations are what we call polarizing. Polarizing basically means they can distort the electron cloud of an anion. So they can pull things towards themselves. This is going to weaken the bonds in the carbonates. It's not going to weaken the bonds between the cation and the anion. It's going to pull on the oxygen-carbon bond and it's going to weaken that bond. So it's going to pull the oxygen away from the carbonate to leave behind the oxide and carbon dioxide. And as before, the smaller and the more highly charged this ion is, the more polarizing it is. The more it is able to distort the electron cloud and weaken this bond in the carbonate. So if we compare group 1 with group 2 is going to be more polarizing. Why? Because it's smaller and it has a higher charge. So that smaller ionic radii and the higher charge means they are more polarizing. and it's that polarizing ability that determines the thermal stability. So therefore, the group 1 would have the more stable carbonates because they are the least polarizing. So group 1. So we have this larger ionic radius, the smaller charge, therefore they are less polarizing, less able to distort the electron cloud around the anion, and therefore more stable. And this also explains why the thermal stability of carbonates increases as you go down the group. So it increases. As you go down the group, whether it's group 1 or group 2, the size of the ion increases. The charge stays the same, but the size increases. So remember, the larger the ionic radius, the less able the cation is to polarize the anion. So these carbonates can be decomposed by heating and will form a carbon dioxide and leave behind the oxide. So the way we can show that the carbonate has decomposed is to bubble any gas given off through lime water, and the lime water will turn cloudy as it makes calcium carbonate, that insoluble precipitate. The quicker the lime water will turn cloudy, the faster the rate of decomposition and the more polarizing the cation. So the quicker that lime water turns cloudy, the quicker the carbon dioxide is given off, the easier the carbonate will be to decompose. So if we look at the reaction that's going on, you've got lithium carbonate. Don't forget it's Li2CO3. There's no other reagents. You're not reacting it with oxygen. You're thermically decomposing it. So this is not a reaction with oxygen. This is simply heating it and seeing if it will fall apart. And it will, and it'll make lithium oxide and carbon dioxide. Nice simple one. Magnesium, very similar reaction. Again, magnesium carbonate decomposing to form magnesium oxide and carbon dioxide. Now, of those two, you would expect actually magnesium to decompose the easiest. The reason for this is it comes down to the charge. So magnesium has a higher charge than lithium, although in terms of ionic radii, the magnesium is slightly larger, but that's outweighed by the fact that magnesium has a 2+ charge. So because it has a higher charge, even though it's got a slightly larger ionic radius, it is more polarizing, and that will result in the faster decomposition of the carbonate. So this is the experiment you're going to carry out in class, and it's the effect of heating on the carbonates of group 1 and group 2. There are a couple of safety precautions you need to take. Firstly, you need to be careful that you're not heating any of the clamps or the test tube holders here, that you're heating the carbonate here. So I'm just going to draw a little arrow and have heat there. The other thing you need to be aware of is what we call suck back. As you're heating this tube, you're going to see some bubbles here. Now initially that's not carbon dioxide, that's just the air being heated up and being pushed through. So just seeing bubbles is not an indication that you've got a decomposition going on. You have to actually wait for the lime water to turn cloudy. The problem comes when you stop heating it. So if you take this heat away and the end here is still underneath the lime water, the air inside the apparatus will cool. It's a sealed system, so we're not letting any carbon dioxide escape. But this air inside here will cool, it will contract, it will draw lime water up the delivery tube. You run the risk of that cold lime water coming into contact with the very hot glassware. At that point it can crack. You do need to be able to draw this apparatus. Notice that we draw it in cross section. So here I have my bung and I can see my delivery tube going into the apparatus. So I don't cross that off, so I need to show that it can work. I don't show clamps. I have everything, if you like, as a freestanding unit. I have to make sure my delivery tube goes into my lime water and I indicate where I am heating it. I don't need to draw a Bunsen burner. An arrow with the word heat is sufficient. So this is an experiment you're going to do in class, and you should see that the lithium carbonate decomposes fairly easily, but the sodium and the potassium carbonate, it's very difficult to get them to decompose. Neither of them should technically decompose in a Bunsen burner flame. Quite often you will see some of the sodium carbonate decomposing. That's generally speaking because it's been contaminated with sodium hydrogen carbonate. Same thing for the group 2 carbonates. Again, you would expect magnesium carbonate to relatively easily decompose. Calcium carbonate usually can decompose. It's quite difficult, but it can be done. But barium or strontium can't. Notice we don't have beryllium carbonate on this list. The reason for that is beryllium is such a small and polarizing cation that actually beryllium carbonate is not stable at room temperature. So as you go down the group, the stability increases. That doesn't matter if it's group 1 or group 2. You should notice that in terms of the stability between group 1 and group 2, group 1 are more stable. They both react in the same way. They thermically decompose to give off carbon dioxide and leave behind the oxide. So on the next page we have 2 diagrams that we've drawn for the thermal decomposition, or rather 2 diagrams that students have drawn for the thermal decomposition apparatus. And there's something wrong with both of them. Pause the videos and circle what is wrong with these equipment. So there's problems at this end. So this is sealed. It can't be sealed. There must be somewhere for the gas to escape. Also, notice this delivery tube here does not go into the lime water here. However, they did pick up 1 mark because this end of the apparatus, the carbonate end, is correct. So this is the second diagram, and this didn't score any marks. There's several problems with this. Firstly, you don't need to draw clamps, you don't need to draw Bunsen burners. They are irrelevant and they just take time and don't get you any marks. The problems with this are this end here. This appears to be a sealed tube. Remember we talked about being cross-section. I'm not seeing the bung actually going into the carbonate. And again, we have the same problem we did in the previous diagram. This end appears to be sealed and there is no delivery tube going actually into the lime water. So that scored 0. Here is the perfect diagram. This is what you should be drawing. So heat, that's quite acceptable. You've got your solid cross section here with your bung, with your delivery tube going through your bung, going into the lime water. And they've even drawn a couple of little bubbles here to represent the carbon dioxide gas coming off. It's nicely labelled, simple and quick to draw. So that finishes this video, just looking at the solubility and the thermal stability of the carbonates. In the next video we're going to be going on looking at the thermal stability of the nitrates, which follow the same pattern as the carbonates. We're also going to be looking at flame tests. So until then, take care, stay safe, bye bye.